Hey there, Math Moment Makers. It's Kyle here, and I'm excited to spend a little bit of time with you here today in developing our number sense fluency and flexibility. But we're going to do it in a way that maybe isn't something that has been on your radar. It's through the curriculum, through the standards that we have to teach. Oftentimes, we educators, I've been there, I've done this before where I was like, I wish I could just focus more on number sense. I wish I could just focus more on students building their number fluency, their multiplicative reasoning skills, their ability to, remember math facts, right? Some of those multiplication and division facts that students don't bring with them, or just to get them, being able to calculate things like percentages, if they're in the store. We often look at the curriculum and our standards as a means of sort of delaying us, or even almost like restricting us or refraining from giving us the opportunity to explore number sense as deeply as we'd like to. And really what I'm hoping to do in this particular video is share how we can actually use these standards that we have to teach, or the expectations as they call them here in Ontario, how we can use those as a means, as sort of like another excuse for students to be able to build their number sense and their flexibility. So let's dig in, and we'll see you on the other side of our quick little intro video. All right, so you are eager to dive in here. One thing we're going to ask you to do before we go any further, do us a huge favor, hit that subscribe button, hit the notification bell. We try to release a video every single week on the YouTube channel. You'll notice that on the YouTube channel, we also have our podcast episodes, which are also dropping each week. That means there's 2 videos every week minimum that you're going to have access to in order to elevate your teaching practice and your pedagogical and content knowledge for your math classroom. So let's dig in here. I'm talking about number sense. I'm talking about fact fluency. Let's look at how we can do this. So as I mentioned, I want to look at the expectations or the standards as a means to build fluency. What that means is we're going to have to ask students to kind of push that calculator away, and we're going to have to look at the concepts that we're learning. We're going to have to be very intentional about the questions we're asking them as we go, so that they can both build the fluency as well as the conceptual understanding of these new concepts, this new understanding that we're hoping that they will take with them. So what I'm going to do is I'm going to bring us over to our problem-based math lessons section of our website. You're going to notice we've got a lot of them here. If you haven't been here for a while, we have over 30 full units that are built out. And really what we're trying to do is we want you to see that problem-based learning isn't something that we just drop in here and there. We actually use the problem-based learning lessons as a means to introduce new concepts, new topics, new standards. And we also use them as, again, an excuse to build fluency and flexibility. Each of our units has purposeful practice built into them, as well as math talk prompts, and many of them are very visual. So today what we're going to be doing is we're going to explore this Pop Goes the Volume unit. We've released it recently. We've talked a little bit about it on a few other of the past videos, but what we're going to be doing is we're going to be hopping over to day 2, where it isn't a problem-based math lesson. On day 1, we introduce a problem-based math lesson where we explore, we do an investigation involving cylinders. We try to emerge, how we can determine the volume of a cylinder. And then on day 2, we're trying to build this fluency and flexibility, but not only with the volume of a cylinder, but also our understanding of the area of a circle, the circumference of a circle, pi, as well as building our number sense as we do this. That means that we're actually going to be shoving the calculator aside instead of doing what I did for a really long time, which was, hey, we're calculating volume, plug and play into this formula, and out comes an answer. That's not what it's all about. We want to use this opportunity as a means for students to leverage the strategies and the models that we've been trying to develop all throughout their upper elementary and their middle school years so that they can actually build this fluency and flexibility so that those math facts are stronger and just their general sense of number is improved. So we're going to be doing this through a virtual setting. So it was a virtual classroom, and actually was a virtual classroom that I was in where the students couldn't actually all chat due to privacy reasons. So you're not going to hear the students or anything. And actually, I can't even hear the students. They could chat with me individually, but not as a group. So you're going to see how this was led in a virtual classroom. However, if you're in a face-to-face classroom, we're going to run it in much the same way, except we're going to make sure that student voice is front and center. So you'll notice that any pauses or gaps in the lesson have been edited out so that you're not sitting there hearing nothing. And you will see sort of the prompts and the responses that I'm sort of sending back to the group as we try to nudge them along throughout this particular number talk, which is a very visual set of number talk prompts. And this is the one we're going to be starting with the group, where students are given this very, very, very short cylinder. It actually is 1 centimeter in height. And we want them to essentially sort of make this connection between the area of the circle and the fact that the area of the base will actually give us, or help us find the volume of the base layer, which we can then use to find the volume of any cylinder with the same base. Okay, so that's what we're going to dive into. Let's dive in now, and I will see you on the other side of this particular video lesson. So, if I recap sort of what we did last time for friends, again, you don't necessarily need to have been here for this investigation, but we were looking at some, cylinders, and, we had some questions. In particular, we were talking about popcorn, like if you could use a piece of paper to create a cylindrical container, like you see here, these cylinders, we were trying to figure out, like, it's the same size paper, which one holds more? And we found that actually, like, the shorter, wider cylinder actually held more. And we sort of came to this conclusion that, as you make a circle wider, you're not just making it wider in one dimension, right? When the height of the cylinder is getting taller, it's only going up in one dimension. It's only increasing in one dimension. But when we're talking about how wide a circle is, like when I make that circle 1 unit wider, I'm also making it 1 unit taller. Like if you picture that there's like pen, like ink at the end of this, and I just spin it around, like you can see this circle, right? When I increase the diameter of a circle by 1 unit, I'm increasing almost like its width and its length at the same time. And when we do that, it's like I'm getting, like, it's having a bigger impact on the area. Like think about a rectangle. Like if I take this rectangle and I say it has an area of 1, 2, 3, well, when I add 1 more unit of length to it, I only get 1 more square of area. But imagine if with that rectangle, if I was actually adding 1 this way and 1 this way, you'd be getting a lot more area. So with a circle, that same idea is happening. Like this circle is only this wide and this tall, or the length and the width of it. As soon as I add that 1 extra unit, it's like, now it's got a second dimension that's being added without even maybe necessarily realizing it. So this for me is something that I went through my whole life and I just never really thought about that, never really had to think about that. But now when I look at a cylinder, I'm constantly thinking about it, and I'm almost like giving an unfair advantage to the width of a cylinder. Like, so if you ever have a container and you look at, you go to, let's say, a vending machine, and there's different, bottle sizes. And if you couldn't see how much was in it, you couldn't see how many milliliters or liters were in this bottle, you could look at the dimensions of the bottle that are oftentimes very cylindrical in nature. And it's okay to have like a shorter but wider bottle, like in many cases, you're going to actually be in better shape. Okay. So that was something that we sort of discussed and we had explored. So today, we also explored this idea that like if we think about the base layer of our cylinder, and we were to just take that cylinder and like we were just to add layers of it, like if we can figure out essentially the area of the base or the base layer, so we could say like the volume of the base layer, and we just scale that base layer up, we will get the whole volume of that cylinder. That is a huge thing here. So I wonder, maybe we could get warm with our friends. We're going to go no calculators here. We're not looking for exact answers. Some of you who have been with us before, we explored circles in the first week we were all together. So today we're going to kind of recap a little bit of that, but apply it to some of our learning from cylinders. So let's have a look here, and I want to give you a bit of a visual here, all right? Here is a circle, and I'm going to tell you that it's about 15 centimeters long. Now, mind you, I don't really care. It could be 15 centimeters, 15 cubes, 15 kilometers, whatever you want, 15 miles. It doesn't really matter to me. But what I'm wondering is, like, can you help me to try to estimate the volume of a cylinder that only has 1 unit of height? And I'm going to give you a little bit of time to think about this. I'll also give you a top view and a side view of this. So again, without a calculator, I'm wondering what might be the approximate volume of this particular cylinder. And most importantly, in the chat, let us know, like, how might you go about doing that work? Okay. Now, I want to just sort of remind you, like, there's some different strategies that you might think about. Like, if I think of this as like 15 centimeters, the radius is 15 centimeters here. Like, you know, you might want to do some estimating to figure that out. Or maybe there's another strategy that you recall from the past when we explored circles, and maybe you explored circles with your homeroom teacher. So I'm going to give you a little bit of time to think on this. Let's give you like, I'm going to say like 3 minutes to kind of like think this through. And then we'll go through this one as a group and see whether any of these strategies that we might emerge could be helpful for you. So let's go ahead. I'm going to throw a timer up. Let's give you some time to think. I'll just toss this up here. And remember, waiting for us to kind of tell you or show you is not a very helpful strategy. It's not very helpful for you in the long run. So let's see what we've got here. I am looking at this thing and I'm checking our chats out, and I see a couple typers, which is great. Keep those thoughts coming. Miss, if you have any folks who have typed or are continuing to type, let's get them going. Oh, I love it. Can you tell me more about this idea that you reference? Mm-hmm. I love this thinking, by the way. I love it. I love this thinking. So, okay, so for those who maybe you're new and you weren't with us for that learning, or, you know, maybe your teacher has done this, but maybe, you know, you weren't with us when we explored this. But yeah, we learned about this relationship between, so this right here is the radius, and this right here is the diameter. And we learned about the diameter, the distance across and the distance around any circle. Like for those who are with us, like we were looking at glasses, right? And we were making estimates around like how many times around the top and all of those things. We did all kinds of fun things. And we learned that it was about 3 times to get all the way around the circle, which I think is super cool that some friends remembered that. So did they say it was about like 90 units in length? I love it. I love it. And I'm going to leave 90 just because, like, to me, it's like easier to work with. but like 90, low 90s is definitely more accurate, right? So I would say like they're more accurate than I'm being right now, which I think is great. Yeah, like I'm looking at this and it's like, now mind you, these are not, not to scale here, but if we were to just kind of use this as our measure and went, yeah, like I'd need 90 to get around. So this is a different unit, but it's like our goal is to kind of figure out like how much of the base would this cover, right? Like we kind of did this yesterday. And really when we look at it, we could say, oh, like if we look at the top, it's like the area, right? It's like 1 square, 2 squares, 3, 4, 5, 6, 7, 8, like 9 squares. But if I want to think of it as a base layer, it's almost like it's like 9 cubic squares. So it's like this is a volume if it's cubic. It's an area if it's two-dimensional, if we're just looking at the squares instead of at cubes. So that's a really interesting strategy. So I'm wondering, it sounds like we need to find the area of this. This is okay if we're using these units, but we're actually using like a different number of units. Now, mind you, I could use these and I could model like 15 of these for the radius, like that's going to be a big circle, lots of these. That would work. I just don't have enough of these to be able to do that personally, but maybe you do at home. So I'm wondering, can we think back? Like, I don't remember a formula for the area of a circle. Like maybe some of you do. That's awesome if you do. Rock and roll. Remember, no calculator though. You can use that formula if you'd like. I'm wondering, can I make this shape look more like a shape that I know how to find the area of? What do you think? Like, Miss, are there any like area formulas that you just know it's like almost like impossible to forget? Length times width is the area of what kind of shape? I love it. So like imagine this, for those who are with us, when we were doing circle measurement, we were like, wait, if we take this, we like chop it into a bunch of pieces. And I'm going to use yellow so it's not like super, like super distracting here. But like if I was to take this, and remember we were saying like, well, if I chopped it into like pizzas or pizza slices, it's like I could rearrange the slices. And as I chop up this into more and more and more slices, what I end up doing is I get, like it becomes easier when I rearrange them to make it look more like a rectangle. Like if I keep chopping this more thinner, get the microscope out and go really thin, it gets to be looking like a lot like a rectangle. Now, I'm not going to say this is like to scale because it certainly isn't. I would have to cut these up and kind of measure them out. But here's my wonder though. Okay, and I'm going to use like a different color here. I'm going to use like orange along the crust of this pizza. I'm wondering, where does that orange go when we take the slices and we sort of put them together? And I'm even going to like draw in. It's like I've got like a slice here, right? There's the crust. And then I got another slice here. There's the crust. Like another slice here. There's the crust. Now, mind you, my slices are horribly, they're not to scale. They're not to scale at all. I apologize. I'm doing my best. But like, where would this orange go? Miss, do you remember where the orange goes? Like if I look at this slice and if I like kind of was to take that slice and put it right there, where is the orange part of the crust? Like, where is that? Yeah, I don't think it's the whole thing. Like, if I look at this, if I cut this out, yeah, like, look at this. If this is the crust, and that's the crust, and that's the crust, and that's the crust, and I look at where the crust is on these slices, it's like, there's the crust, there's the crust, there's the crust, there's the crust. There's the crust. Now, mind you, it's not to scale. Okay. Well, let's talk about this first. So if this is our circumference right here, and like half of the crust went up here, half of the crust went down there, what's half of my circumference? Like I took like half of 90 and I put it up here, and I took like the other half of 90 and I put it like right there. Like, what's this length gonna be? What do you think? Half of 90. I love I I love your strategy there where you kind of worked your way up and you like doubled 30 to 60. You're like, okay, now I have another 30 that I need to worry about. And I'm like, oh, half of 30 is 15. Add that on. I love it. That's a great strategy. So this is 45. This is 45 centimeters. I'm wondering, like, where is the side of each slice? If I look at like how long the side of each slice is, yeah, tell me, like, what do you see? What do you see? It's like the slice edges. Look at this. It's like each slice edge is this part right here. It's like I've got all these radii or radiuses. Holy smokes, that is bonkers. So I could just take this 15 units and say, you know what? This right here is 15 centimeters. So I look at this and I go, well, wait a second. If this is 15 and this is 45, if I clean this up a little bit, I feel like I can find the area. Now, mind you, I don't know what 45 times 15 is, but there is something I do know. Like I feel like if I break my 15 up into 10 and 5, like, so if I do it in chunks, and maybe, I don't know, like maybe I break up my 45 into, look at that. How awesome is that? I don't know about you, friends. Some of you might want to break this up into like 10, 10, 10, 10, like 4 10s and a 5. Or some of you might be like, you know what, like 40 and 5, that's not too bad. And then I look at this and go, well, wait a second. Instead of trying to like do all of this work at once, like instead of doing this all at once, I could like break it up into more manageable chunks. Like, Miss, do you know what like 10 times 40 is, or 40 times 10? I got 400. Now, this is now an area of a mini rectangle within my bigger rectangle. So this is centimeters squared, right? Here was centimeters, here's centimeters, centimeters, centimeters squared. How about over here? Like, what's this chunk going to be? I've got a width of 5. Love it. 10. So that means this is 10, and that's 50. I love it. How about right here? Where are we looking for that? I love it. And like how I always look at it, I go, okay, well, when I do that, when I use like, a pattern that I've recognized, I think of it, I go, well, like 5 groups of 4, but what is 4? It's like 4 10s, 4 10s. 5 groups of 4 10s is 20 10s. So it's like I've got 20 10s. Boom, I'm done. And then I've got centimeters squared. Over here, I got 5 centimeters by 5. Oh, that's not too bad. 25 centimeters squared. Holy smokes. If I put this all together, I think I've got an area for my circle over here. What do we have here? 400. So 400s, 200s. That's 600s, 650, 600s, and 675 centimeters squared is the area of this rectangle, which is the area of that rectangle, which is the area of that circle. Holy smokes. Now, some people are back there. Like, first of all, if you're like feeling a little mind blown, give us like a surprised emoji out there. Give us a surprised emoji. Some of you might be like, why don't we just use the formula? If that's you, give me an applause. You're like, why don't we just use the formula? The reason why is I just want you to note the formula is hidden inside of what we just did. So if you know the formula, rock and roll. But I promise, if you just know the formula and you don't know where it came from, you're going to be like really, like one day you're going to get kind of stuck. You're going to be like, I don't remember the formula. Like this happens all the time in math class. Yeah, like totally. And I do want to kind of make you aware, my friends, for those who are like you're like all over the formula. Like this is the formula. Look at this. 15 was our radius. 15 was our radius. So it's like there's the length of this rectangle. And actually look at when you and it might be easier to see up here with this one, with our friend up here, just because the 45's all together. But look at this for a second and think about this. Wait a second. There's a radius right there. There's like another radius inside of here, right? There's a 15 inside of there. So like I could literally split this up and go, okay, well, there's a radius here, another 15. 30 is another radius. 45 is another radius. There's like 3 radii there. Plus, remember, we rounded. There's actually a little bit extra that we didn't really pay attention to. So really, if I look at this formula and I go, wait, that's the radius. It's the radius times the radius. Okay, so you're telling me the formula is, okay, it's a radius times the radius, which is radius squared. Plus another radius times the radius. Okay, that's another radius squared, okay? And then plus another radius times the radius, which is another radius squared. And my friends, look at that. It's like 3 radius squareds-ish. But remember, we had a little extra. It's actually 3.14 times the radius squared, or pi r squared. Like that's the formula. And it comes from what we just did. That is sort of a quick little summary of like why this method works. So my question now comes back to, okay, we found the area of this base layer. So what's the volume going to be then? If the area is 675 centimeters squared, what's the volume then of a 1 centimeter tall? So like one layer. It's like 1 unit layer of this cylinder. It's like a super not realistic cylinder. Like you probably won't come across a cylinder like this too often. But in reality, it's like, oh, like that cylinder, like this cylinder is actually going to be 675 centimeters cubed. It's like we found the volume pretty much by simply finding the area because there was only one centimeter of height. All right. So kind of giving you like a bit of a visual here, right? We found our circumference. We knew it was like about 3 times as big. It's actually 3 and 14% times as big as your diameter. Okay. If we split it up into that pizza, here's what we had, right? We found like half of the circumference goes here. Half of the circumference goes there, right? Which is, in this case, 45. And then all we did was we were like, all right, let's find the area of this rectangle. Go for it. You know, we chose to use a similar strategy to what we saw here. We did this work and we found our total area, which is the total area of that circle. And guess what? The volume is simply the cubic units of the area quantity, right? That's 675. Holy smokes, mind blown. Now, we could stop there, but I'm curious. Who can help me figure out the volume? If I take the same cylinder, we know the area now. We know the area of this base. What if I was to say that the cylinder was actually 15 centimeters tall? Same base, but now our height is not 1 centimeter. It is 15 centimeters. I wonder, can you help us figure out what might the approximate volume of this cylinder be? And remember, we know the volume of the base layer. Let's give you a little bit of time here. I'm going to give you about 4 minutes. I want you to, again, without a calculator, do this work. If you're there and you're just sort of like, yeah, I'll just wait for them to show me, it is not worth it. It totally is not worth it. You are giving up a learning opportunity for your brain. And I would argue that that is a huge missed opportunity. So give it a shot. Let's fire a timer up here for you. And we'll be back to hang out with you in just a couple minutes. Okay. And does that square kind of represent, you think, like looking at the cylinder like sideways, like from the side? Awesome. And then up the side is 15 centimeters. And, you know, dare I even mention, it's like almost like to like right there, there's that like base layer, right? The base layer would be like 675 centimeters cubed there, that base layer, eh? Ah, that's hard. I don't like that. I personally can't do that. So you said this strategy though of kind of using an area model. So it's area because we're looking at it on like a flat page, but you're kind of looking at this volume with an area model. Tell me more about that. I love that. So 600s and then like 75 sort of left over. You notice how like I'm not like measuring this to be like 75, like I'm guessing it's probably even smaller compared to 600, but it's okay. I'm leaving a little bit of room. I love this idea. Okay. Got it. So it's like 15 is broken up into 10 and 5. I'm going to just assume the 10 went there, but it could have went down here. It really doesn't matter. Oh, cool. All right. So I'm going to do one of these. So it's almost like we're breaking down, we're decomposing both quantities to make them more friendly, which I really like. And now remember, like this is like, you know, it's hard to picture because it's a rectangle, but it's almost like you're looking at this cylinder sideways. So like if you look at this cylinder sideways perfectly, it kind of looks like a rectangle, right? Like if it has that perfect sideways look to it. So this is really volume we're working with, layers of volume, but like we're looking at it using a helpful model. Okay, so we have 10 groups of 600. Love it. So we've got 6,000 centimeters cubed. Super cool. Ooh, 3,000. So remember we were like 600s, 5 times, or 5 groups of 600s is 30 hundreds. Super cool, which is 3,000. I love it. Okay, so I'm thinking like I got 10 groups of 7.5 tenths. That's kind of what I look at. It's like 7.5 tenths. That's 7.5 tenths, like, or not tenths, tens, I should say, tens. Okay, so that's 750 and 5 groups of 7.5 tens. Whew, 375. Some people might have split this up too, right? Like you could have went, okay, 600, 70, and 5, and you'd have like an extra column and you'd just have it broken up a little bit further. If we put this together, like dare I mention, like I feel like that is what, 9,000? Which I feel like I'm looking at it going like, okay, that kind of makes sense. Like I know 700s and 300s is 1,000. So I know that's 1,000. Then I have 50 and 75. And I'm like, well, I know there's a 50 in a 75. So that's 100 plus a quarter left over. 125. Yeah, that's pretty good. And then all together, holy smokes. And remember, this is cubic centimeters because like basically we're taking this right here is like an area and this is a single dimension. But when I take an area and I multiply it by another dimension, I get the third dimension. Like that is like, whoa, holy smokes. That, my friends, is such a cool strategy for how they did it. And just to kind of, again, like reiterate or help you visualize this work, it's like you're taking this, you know, this big cylinder with this base layer. Remember, we had this base layer and we just need 15 layers of it, right? Like 15 more layers of that. I could have just repeatedly added that over and over and over again 15 times. I'd get the same place, right? So if you want to do that, rock and roll. Maybe you did do that. Some of you may have like said, well, I want 10 of those. And maybe that was easy for them. Okay. And then they're like, now I need 5 of those. And it's like, oh, maybe like take half of 10, if you can half that, and then you can put that together. This is just a different way of getting to the same place. Remember, we did estimate here. So if you took all the formulas out of your math textbook or whatever, like the answer is not going to be exact, because remember, we estimated the circumference right from the start, right? So like we did make some estimating, but the whole goal here is like, if you can envision how to do this without a formula, holy smokes, you have a clear understanding of the math. Miss, what do you say we give them one more to try on their own? The whole thing, like the whole thing. You got to find the base layer of a cylinder. Then you got to like scale that base layer up. Remember, basically, we're dealing with volume. It's area of the base to help you figure out what the base layer is. And then you just figure out how many layers you have, and you multiply those, and you're rocking and you're rolling. So here's the cylinder I want to give you without a calculator. All right. Have at her, my friends. Remember, we know the circumference is a little more than 3 times the diameter. Use that and follow your pizza nose. All right, we'll give you a little bit of time. We'll come back in about 5 minutes. Are we ready to rock and roll? My friends, we're looking at the time. We don't have much time, so I'm going to share some possible strategies. It might not be the strategy that you used, which is totally fine. But when we're looking at this particular problem, we could approach it by, once again, looking at our base layer and starting to think about, what area does that circle cover? And remember, chop it up. We know our circumference is about 3 times as long as our diameter. Chop it up into pizza slices. And here we are. We've got a pizza with a width, which is the radius, the edges of our pizza, and our pizza crust is split amongst these 2 sides here. So half of our circumference. Break it down however you choose in order to figure out your area. And if we know the area of the base, we know the volume of the base layer, right? This is a big thing about, it doesn't have to be circles. It doesn't matter what volume you're dealing with. If you know the area of the base, you know the volume of the base layer, and you're good to go. And then from there we go, wait, how tall was this cylinder? If I know the base layer, I know a 1 unit tall cylinder is 75 units cubed. A 2 unit is going to be double that. A 3 unit is going to be triple that. A 5 unit is going to be, is it quintuple that? Is that right? I'm not sure. Multiplying by 5? I really, that's risky. But look at that. I could also use, once again, a very similar model to get, I've got my base layer. I've split it into friendly numbers. And I've got this volume. I've got that volume. Oh my gosh. I've got the volume of this whole cylinder. My friends, however you choose to do it is up to you, but I don't want you to forget how this actually is working, because that will be the key for you. I hope when you go back to your classes next week, you share some of the learning that we've done here over the past 3 weeks. Miss, my brain's bigger. I know your brain's bigger. And I know all the students who have been participating and doing this work, your brains are all bigger as well. Keep on going. And I want to thank you all again for letting me hang out with you here over the past couple of weeks. Well, Math Moment Makers, what did you think? Hopefully you found that the way we structured this particular visual math talk was a means to not only allow us to access the conceptual understanding of the standards or the expectations that involve the volume of a cylinder, also gave us an opportunity to revisit our understanding of the area of a circle conceptually and the circumference of a circle conceptually. You'll notice that we didn't really rush to a formula or an algorithm here. And what we really wanted to focus on was how can we make estimates utilizing our our tools and our strategies that we bring with us. And today we leverage the area model quite a bit. So we're using an area model to help us find volume calculations. So just keeping in mind, you can almost look at it as a volume model if you want to think of it that way. But ultimately what we're trying to do is help students with their multiplication and division skills and that sense of number as they continually build their understanding, both conceptually and procedurally, with formulas like the circumference of a circle, the area of a circle, the volume of a cylinder. So hopefully you found it helpful. Remember, all of these problem-based lessons are there and available for you. So over on our website, if you head to learn.makemathmoments.com, you will see up at the top our tasks area, and you can dive into any of these tasks, noting that this particular unit has 6 full days there available for you, both of problem-based as well as purposeful practice, as well as visual math talk prompts that you can leverage in your classroom with your students right away. Of course, Academy members have the advantage of downloading some of our printables and the full slide decks if you don't want to run it from the web like we're doing here, as well as the full teacher guide. So dive in, have a look around, and if we can help at all, please let us know. And if you've made it this far in the video, do us a huge favor. If you haven't yet, make sure that you hit that subscribe button, hit the notification bell, and leave us a comment. Did you learn something today? Is there something here that you might leverage to bring into your own classroom? Or is this old hat? Maybe you've been doing this stuff for quite some time. Either way, let us know. We love to hear from the community, and it helps us to figure out, hey, what can we share with you in the next week's video? So have an awesome day, and thanks for hanging out with us. Math Moment Makers are awesome, and we will see you in the next video.